we now learned regression allows us to predict continuous variables. Now we will use regression technique to predict a player's overall performance based on their attributes. For this, we will use the soccer data set from back in week 1, where we've seen that overall analysis. Over the last 7 weeks, you've learned quite a bit. So we'll do a more hands-on analysis of this data set. We are ready for that now with the tools we've learned. Let's locate our notebook. It's called European Soccer Regression Analysis using scikit-learn. It's in your folder for the week along with the data set it needs. After you open it, let's get started by importing the libraries. Before we import our data set, we'll import our libraries. Just look through them quickly. We have some regression methods imported there. The pandas, SQLite, which is to interact with a relational database, which is the data set for this. But we'll learn more about that next week in week 8. And some other mathematical and error detection related modules. Okay, let's import these libraries. Now we'll import the data set into a data frame. Okay, and then let's check out that data frame. What we are doing here is we are connecting to the data set, and we are using this connection to select the player attributes and load them into a data frame called df. You might have noticed by now that once you get used to the data ingestion, it is always similar functions to ingest the data into a pandas data frame. So look at other example notebooks, the example notebooks we gave you, and that should be enough for you to find the data set and load that type of data into a pandas data frame in your exercises and things like that. So let's look at the first 5 rows of this data frame to familiarize ourselves with the data. We see that there are some features related to players, right? Overall rating, potential, preferred foot, attacking work rate, defensive work rate, and things like that. We can look at the shape of this function, the data frame. So I'll say df.shape. We see that there are about 42 features, a little less than that with the identifiers. Let's declare a list of these features. Yeah. We can say df.columns. We could see all of them, right? So now we'll select some of them. We'll select the ones we want to use for predicting the overall rating. After this video, of course, you can further play with this list and reduce it to see the effect on the accuracy of predictions. But for now, we'll use a lot of these features to get started. Except here, we won't see the overall rating, because that's our prediction target. Based on the input data from these features, by selecting them, we will predict the numeric overall rating value of a player. So let's do these declarations of the columns in the feature, and target will be named overall rating. Let's now start cleaning the data. We'll simply drop the null values. As we know from week 1, this is an issue with this data set. We'll use the data frame and say df.drop NA. Now we have a slice of the data that doesn't have null values. Let's now create the 2 data frames. Like you're used to it now, we need an x, the input, and a y to go from, with the analogy again of y equals fx, with features and target values. X will be our input data frame, and we'll select the features we wanted. We declared in our features list. We'll load the data frame without the null values now into X with those features. Feel free to stop and look what's in X and what's in Y if you're getting confused. And but we are doing the same operation we've been doing in our earlier notebooks for machine learning for this week. Let's look at a glimpse of the data. We print one row for X, let's say 2. We see the values in the X data frame, the potential, crossing, and things like that. We can also displace Y to see the range of values in it, what kind of overall rating scores exist, and we see that it ranges between 67 to about like 77, things like that. 81 we see there. Please refer to the Sucker Data Analysis Notebook in week 1 for further explorations through this data set, and now you should be able to understand a lot of the code cells in that notebook. So now it's a good time to go and have more fun with that analysis. Okay. I'm assuming you stopped the video, maybe did some more explorations. And now I'll start with a regression analysis task. We are doing the same operation using train test split. We are splitting the data set into test and training sets, so we can use one for training and the rest for testing of the regression algorithm. Let's run this cell. We'll perform 2 different modeling operations using different regression techniques. First, we will use a linear regressor. We'll select the features and use a linear regressor to predict a player's overall rating. Here we store a linear regression object right here, and I'll call it regressor. This is the linear regression module we selected from scikit-learn. And we will then use that regressor and give it our training input and label data sets, numeric labels in this case, X-train and Y-train. So using the fit method of the regressor, we fine-tuned the parameters of the linear regressor to capture the interactions between the 2 sets, the X-train and Y-train. So we are trying to fit X-train and Y-train and create a model. We can then use this predict method because we now have a model, a linear regression-based model. We'll use the predict method of that trained model to perform the prediction on the test set, which is our X_test. As a reminder, note that the model has never seen any sample from this test set. So it's predicting on a new data set. Okay, let's go and execute that. And we see a predicted set of values for Y. As you know, we can compare them to the values in the Y test and see how accurate they are. If we look at and describe some things about this data set, we see that the overall mean is around 67.6, and the minimum and maximum are 33 and 94. So we see that the predicted scores are actually within the range with Y test. We can also try to describe Y prediction and compare them, but we'll do something different. We use actually, as we described, root mean square error to measure the prediction accuracy of our regressor. That's the RMSE, root mean square error in short. So RMSE captures the variation of the predicted value, as you would remember, from the observed value. So an RMSE score of 0 means perfect prediction with no errors, which is the ideal scenario, which almost never happens. When comparing two regression models, then the one with the smaller RMSE will be better, since its predictions will have smaller difference from the observed values or the measured values before. So let's check that. RMSE equals square root of mean error, and y true is y test, and y prediction is y pred is y prediction here, which are the arguments that we give to mean squared error function. So when we compute RMSE and print it out, we see that the linear model gives us an RMSE of 2.8. This is a good start, since the range of overall rating is from 32 to 94, with a mean of, as you would remember, approximately 68. Okay, good start. Let's see if we can improve upon the prediction accuracy now by using a slightly more complex model. That would be, let's say, a decision tree regressor. A decision tree regressor builds a model in a top-down manner by splitting data set on an attribute. So the algorithm chooses the attribute which gives maximum reduction in standard deviation. You'll hear more about these in your machine learning course, so I'm going to quickly describe it here and then move on to applying it. Take this, hopefully an appetizer for the upcoming machine learning course. Well, you'll learn all about these. So now let's use the decision tree regressor to capture player performance as a function of, again, their attributes. The fit method performs the fine-tuning again, so we are doing the exact same thing. We have a regressor, but since this is a tree, it has a depth. The maximum depth is 20. And we are using that regressor to fit the training and input and output training data sets, so X-train and Y-train. We change the method, but the fit line stays the same. The regressor will be just of another class and another method. So it's done. We have now a model, and we'll use this model to predict on the test data again. So let's do that, and we see the values changed a bit, right? We have the 66 here and 62 and things like that. To get an idea of the RMSE, we note that a root mean square error of 100, for example, would be too high, because our mean is 68, and our RMSE is higher than our mean value. So let's run this. Again, we can describe the test and do the RMSE for this new the decision tree regressor. So remember, our linear regression operation gave us an RMSE of 2.8. And the decision tree regression algorithm gave us an even lower one, 1.44, which is better in terms of prediction accuracy than the linear model. Again, the RMSE captures variance of the predicted value from the actual value by our system, so it is a measure of how well a model performs against operations. So I'd say an RMSE of 1.44 for a test set that has a mean of 68 for the target variable is pretty good. And the model never got a chance to look at the test set before the prediction. So that ensures our evaluation was on a data set that the model hasn't seen. And we saw that linear regression model performed a little less well than, or a little worse than, the decision tree-based regressor. Great, we finished our machine learning lecture content for this week, week 7. I hope you'll enjoy the test notebooks that we give you and have some more hands-on experience with what we just discussed.